Welcome to the part 1 of the Cloud Autoscaling series. This video introduces the fundamental ideas behind autoscaling, what it is, why cloud platforms use it, and how it helps applications stay fast and reliable even when traffic changes unexpectedly. Before we move on to the load balancing and full autoscaling behavior in later parts, it's important to understand how servers behave, what load means, and why scaling is even necessary in the first place. So, what is autoscaling? Autoscaling is a system that automatically adjusts the numbers of servers based on the real demand. If more users arrive, more servers can come online. If traffic drops, servers are removed to save cost. Without autoscaling, teams would have to manually monitor traffic and add servers themselves, which is slow and inefficient. Cloud platforms like AWS, Azure, and GCP make this automatic so applications can self adjust and continue running smoothly. Autoscaling is especially useful for apps that experience unpredictable or seasonal spikes. For example, e commerce during sales, ticket portals during launches, or mobile apps during trending events. Now we are going to learn about the types of scaling. So, there are mainly two primary ways to scale a system. Uh, what does scaling mean? So, scaling up means upgrading this machine, giving it more CPU, increasing RAM, or using a powerful instance. This is a straightforward but has limits. Eventually, you hit the maximum hardware you can buy. Scaling out means adding additional servers and spreading the incoming traffic across all of them. This is the core idea of cloud autoscaling. You don't rely on one giant machine, you use many smaller machines that can grow or shrink depending on the workload. Scaling out is more flexible and far more fault tolerant. If one server fails, the others can keep working. Autoscaling relies on continuous monitoring of important system signals. Some common triggers include CPU usage. High CPU means each server is working at maximum capacity. Another point could be requests per second. Uh, Traffic surges often lead to the need for more servers. Latency, how long the system takes to respond a user. Queue length, a rising queue means servers are overloaded. Memory usage, too many processes of heavy memory usage. Too many processes or heavy tasks can exhaust memory. Whenever these matrices cross a threshold, the system decides to scale up, and when matrices stay low for a while, it scales down. Autoscaling isn't a single event, it is continuous loop. First, the monitoring system collects matrices, then the evaluation logic compares current values against thresholds. If something looks wrong, the autoscaler takes an action, like adding or removing an instance. Then it waits for a cooldown period. This prevents the system from adjusting too quickly or reacting to temporary fluctuations. This loop runs every few seconds or minutes depending on the configuration, constantly keeping your infrastructure balanced and responsive. There are different strategies for scaling, each useful in different scenarios. Reactive scaling waits until a problem happens, like high CPU or high latency, and then adds servers. This is simple and excellent for learning. Predictive scaling looks at patterns or historical data. For example, if traffic spikes every day at 6 pm, the system adds servers at 5:55 pm before the spikes arrive. Scheduled scaling is completely manual. You instruct the system to scale at fixed times. This is useful for apps with very predictable load patterns. In this series, we focus on reactive scaling because it clearly demonstrates how the system responds to changing traffic. To make these concepts easier to understand, I have created a simple interactive simulation. On the screen, you can see our server instances, a graph for latency and instance count, and a slider to increase or decrease incoming traffic. This is not a backend simulation, it's a visual model that helps us understand how load affects system behavior. We'll use this throughout all three parts of the series. Let's simulate a sudden spike in traffic. Right now, the traffic is low and we only have one server running. Its load indicator is green, which means it's handling that workload comfortably. Now watch as I increase the traffic slider. As the traffic rises, the server load also increases. You'll notice the load bar shifts from green to yellow and eventually red. This tells us the server is getting overloaded. If you look at the graph below, the blue latency line jumps upward, showing that the system is slowing down. This is exactly how real cloud systems behave during a traffic burst. One server simply keep up and users experience delays. Even though autoscaling is powerful, it comes with challenges. Scaling too late causes users to face slow response times. Scaling too early wastes money by adding unnecessary servers. Traffic bursts can overload a system before scaling catches up. Startup delays can introduce temporary downtime. Some servers take time to boot. Non parallel workloads don't benefit much from additional servers. This is why tuning thresholds, cooldown periods, and monitoring rules is incredibly important. In real cloud systems, one major issue is called flapping. This happens when the system keeps scaling up and down repeatedly. Let's simulate that. First, I'll turn auto scaling on and increase the traffic. The system sees the high load and adds more servers. This is good. Now watch what happens if I quickly drop the traffic. If there's no cooldown or if the thresholds aren't configured properly, the system immediately removes the servers. Then, when traffic rises again, it adds them back. This constant bouncing, adding, and removing capacity is called flapping. It wastes resources and can cause instability. Real auto-scaling systems prevent this using cooldown timers and smarter scaling rules. So let's summarize part 1. Auto-scaling automatically adjusts capacity based on load. Scaling out is the most flexible strategy used in the cloud systems. Metrics like CPU latency and request rate determine when scaling happens. Sudden spikes can overload a single server instantly. We saw this in our simulation. Poorly tuned scaling rules can create flapping behavior. Understanding load latency and system behavior is essential before moving to load balancing and full auto scaling logic. In part 2, we'll introduce load balancers and see how they distribute traffic across multiple servers before scaling kicks in. And in part 3, we'll stitch everything together to demonstrate a complete realistic auto scaling system. Thank you.